Hello students, in class 12th I have told you about the electromagnetic waves, their properties and the displacement current, and now I will take the Maxwell equations. Maxwell equations. John Clark Maxwell. Was a mathematician, but he was interested in the study of physics. Maxwell studied the fundamental laws of fluctuating electric and magnetic fields. In 1861 and 1862. These fundamental laws are called Maxwell equations of electromagnetic waves. So these are four Maxwell equations. Four Maxwell equations. These are in integral and differential forms. Both. But here we will give only the integral form of the here we will see only integral form of Maxwell equations. Maxwell equations. So now I write one by one. First equation. Integration, surface integration E dot ds equal to Q upon epsilon naught. And this is the Gauss law of electrostatics. It is Gauss law of electrostatics. E the electric field, and this represents the electric flux, the total charge enclosed by the surface, and this epsilon naught, the absolute permittivity of the free space, and here the Q. Charge Q can be written as Q equal to volume integration rho dV. Rho is the volume charge density. In the 12th class we have studied three kinds of charge densities. One is the linear charge density, surface, second the surface charge density, and third the volume charge density. So we can also express this V Q in terms of this one, where rho volume charge density. This is the first equation of the Maxwell. The second equation. Second equation. This is the surface integration B dot ds equal to 0. This I take in parenthesis so that it could be clear to you. This is the magnetic flux, and you know that this is Gauss law for magnetism. It is Gauss law for magnetism. So you have these two equations, and then now third equation. third equation. Line integration E dot dl equal to minus d phi b upon dt. This is second equation. Third equation. This is second. This is third. And this is nothing but the Faraday law of electromagnetic induction. It is Faraday's law of electromagnetic induction. Here E is the electric field, phi B, this is the magnetic flux. Magnetic flux, phi B equal to surface integration B dot ds. This is what this phi B. And you know that here the induced electromotive force is proportional or is equal to the negative rate of change of magnetic flux. This is what the Faraday's law of electromagnetic induction. And now fourth equation. Fourth equation. Line integration B dot dl is equal to mu naught I plus mu naught epsilon naught d phi e upon dt. If you drop the second term in this, then you will have so much. This is the Ampere's law. But since this Ampere's law is violated or this is not true for the currents which are passing through the capacitor, so Maxwell made some modification that in addition to this conduction current, there must be a displacement current that I told you yesterday. So this expression epsilon naught d phi e upon dt, this is the displacement current, and then this equation was called the Maxwell Ampere's law. So this is the fourth equation. And now it can be had from here that it is called Maxwell Ampere's law. So here the term epsilon naught d upon dt phi e is called displacement current. Displacement current ID equal to epsilon naught d phi e upon d. This is the displacement current. And from this, when he use all these equations in the differential form, then he applied all these to the free space. He obtained the expression for the speed of the electromagnetic waves in the free space. So wave equation. Now I am telling you different from this one. The standard wave equation. This is equal to 1 upon c square del 2e upon del t square minus del square e. This is equal to 0 or 1 upon c square del 2b upon del t square minus del square b equal to 0. These two are the standard meanings. So they show that the variation of the electric and magnetic field with that time. Here I have used this operator. This is an operator which gives us the vector quantity. Where c equal to the speed of electromagnetic wave. And this is equal to 1 upon the square root of mu naught epsilon naught. And if you put these values, 1 upon the square root, this mu naught is equal to 4 pi into 10 raised to the power minus 7, and this epsilon naught, this is 8.85 into 10 raised to the power minus 12, and just you solve it, then this is 2.997 into 10 raised to the power 8 meter per second, or this is equal to 3 into 10 raised to the power 8 meter per second. So the speed of the electromagnetic wave is equal to the speed of light. It is the speed of light in free space. This is what we are getting here, and now this del, this is given del, this term del, this is equal to, this is an operator, the operator del equal to I del upon del x plus J del upon del Y plus K del upon del Z. This is the partial differentiation, and it shows the variation of some scalar quantity in the space. So this scalar quantity gives you a vector quantity. So this is suppose we are having here the electric potential, then del V upon del X, del V upon del Y, del V upon del Z, then this will give you the electric field. So if you are having something scalar quantity that is connected with this one that varies in the free space, then we get a vector quantity, and this relation is termed as the operator. This and gives the in the form of vector form. You can see you are looking here that I, J, K are being used. So this is all about the Maxwell equations, and sometimes they are asked. So you just study all of these, and also they are useful for you to know that what are the Maxwell equations and what is the standard wave equation and what is the Maxwell-Ampere's law or the equation. This is very important. So all this is the basis of Maxwell equations, which were the fundamental laws of the electric and the magnetic fields, which were fluctuating or the varying with the time. So you all like, share and subscribe this video. Thank you very much.